Hello, my name is Bob D. Hilster, and I am your particle model guru. Today we're going to talk about charge as used in the particle model. So what is charge? So the standard model, of course, uses the electron as a subatomic particle that has charge. Somehow it has it. The particle itself has charge. And these are the symbols, E with a minus sign or beta with a minus sign. And the proton is a subatomic particle with a P or P plus showing a positive charge. So they just assign, it just has it. And of course, positive and negative attract and like charges repel. It's all normal way of operating. Well, somehow in the particle model we really have to have a physical property that is a charge. You can't just add a plus or minus. There has to be a characteristic. So I decided to review a list of things that might be a characteristic of charge for a given particle. Okay, so maybe size could be used. A large particle and a small particle. Surely there are different sizes, and somehow these things attract and repel. Or shape. Maybe round shapes attract squares, and two rounds repel and two squares repel. Or maybe it's color. Although I don't know that nature even recognizes color. I don't know how it would, but we humans do. How about if the particle is, one particle is real fast and slow? That doesn't make much sense. How about spin? Counterclockwise one way, clockwise the other way. Hey, maybe. Spin looks good, actually. I tried to make spin work any number of times, but spin needs a medium. There's an experiment done by Ian using cylindrical drums spinning in water, and he can show how they attract and repel. Quite interesting. However, the particle model does not have a medium. There is no ether because the light, we don't need ether for light, which is the main reason for having an ether. And if you had it, then spin might work. But the particle model does not use ether, does not use a medium for light. And so we're stuck with not being able to find a physical property for charge. Main reason why we don't accept charge as being something real. So let's look at two types of charge. First one is dynamic charge. And how are particles stored as dynamic charge? They're stored that way in a magnetic field. G1 particles are stored as they move around and through a magnet, around and through an electromagnet, and a coil, and a battery, and a capacitor, and a wire. I missed a wire. You get magnetic fields, and G1 particles are there. They're being held in place by the F2 force field. They are not just sitting sitting there at the negative terminal of the battery or the capacitor, waiting for a bus to move them. They're just not hanging out. They are already moving at speed c around and through these devices. This is dynamic charge. Static charge. How are G1 stored as a static charge? They're stored in G1 orbitals. There is no physical property of the particle model that limits the number of G1s that can orbit the nucleus. And of course, again, particles just don't hang out in space. And so the particle model can have more G1s stored in the atom than Bohr model suggests. These extra orbitals are how objects gain negative static charge while the loss of G1 represents represents a positive static charge. They're stored in orbitals. They're moving at speed c, somewhere about the speed of c as they orbit around the atom. Okay, so we're going to talk more today about the static charge, and one of the things that is important is what's called the triple electric effect. Okay, on the right is a chart, a triple electric series actually, where it lists objects such as air, human hands, and all the way down to Teflon. These are the types of objects that seem can easily gain or lose G1 particles. And holding silk to glass, and I'm talking about holding it, not rubbing it, but because glass is up at the higher than silk, here's silk in the middle and here's glass, these two objects, when they held together, you get the glass gives up the negative, the electron in the normal expression. They give up the electron, and silk becomes negatively charged, and the glass becomes positively charged. All you have to do is hold them together. You don't have to rub them. These materials have a way of just doing that. So here's the same graph, only I've modified it over here. There's a couple of things that bother me. The first one is Earth is not listed. I'm going to describe an experiment in a moment where Earth ground is a necessary step in doing that experiment. And yet it's not here. You got human hands, they got air, but they don't have the Earth. Maybe the air replaces it, I don't know. On the right of the chart, I've added the fact that I've taken glass and silk and stuck them together and held them together. Particle model would suggest, and I don't know how it builds up around this. I don't know enough yet about how the G2 force field builds up, but you got particles surrounding these two, and somehow there's enough force in the direction from glass to silk to cause the G1s to move from glass to silk. The G1 orbital here moves and becomes a G1 orbital there, just by holding the things together. That's quite remarkable. You can take a balloon and hold it on the wall, and if the humidity is low enough, you might get lucky enough. It's not easy, but you might get lucky enough for the balloon to stay there because it developed a static charge, not caused by the triple electric, but described by that effect. Okay, so here's an experiment with static charge. Let's take these elements of our experiment. Have a conductive table connected to earth ground, a glass rod, a silk cloth, and you're standing there, and you're going to do this simple experiment. You place all objects on the table, including you. That should discharge everything. That's what's normally stated. If the conductive table is grounded to earth, ground, when you place these objects and when you touch the table, everything becomes discharged. And when you then, so this is one thing that is important. And the question is, what does this mean that you're discharged? So if you cause any object to touch another object, there is no spark. There is a balance. Even though each object has a different F2 field around it, because they're different objects. The table's different than the glass rod, than the silk cloth, and different certainly than you. There's an F2 force field around you, but when you touch everyone to ground, those force fields around the whole system that we're talking about, all around all these elements, and it is got a force field, and around each item it has a different force field, and yet there is a balance. And that balance in the F2 force field keeps the G1 particles, it keeps the G1 particles from moving, or at least having a net motion. There might be incidental changes between the objects, but there is no net change of G1 particles from one object to the other, even though you've got this varying, what looks like a varying force field. This is not a homogeneous force field. It's got a distribution. But when you pick up the glass rod and the silk cloth and put them together, the F2 force field changes. You've changed things. You've moved the two together, and the triboelectric effect takes place where the F2 force field changes the G1 part. The F2 force field changes, and the G1 particles will begin to move in the direction indicated by the triboelectric effect. These are known facts, done and tested. So it's the F2 force field. When there's a balance, there's no motion, there's no spark. When you take the glass rod and the silk cloth and put them together, the force field changes, the movement of G1s happens. Then if you further rub the glass rod with the silk and you quickly pull them apart, you have enough of a static charge build up that you could actually get a spark. So when the G1s move, they move at speed c. When they move from glass to the silk, they move at speed c, and some will just move straight out into space. Once they're released and gone, they're in space. Or they could be scattered by hitting another G1 or hitting a nucleon and scattering off into space as well. Or they're trapped by another atom. This trapping is when they become a G1 orbital. These charges just don't hang in space. And atoms can gain as many G1s as it can hold. There is no limit. Some of these G1 orbitals may collide with another. Well, once you have too many, let me put it that way, some of the G1 orbitals may collide with one another, with another G1, and they both scatter until the atom becomes more stable. This is called a natural discharge of the atoms of the G1s for example, in the silk. So in the particle model, the nucleon, the G1, and the G2, all of them, they have no charge. The particles do not have a plus or minus charge. We use the symbol plus and minus, north and south, to indicate the flow of G1s. But there is no charge. Atoms and molecules can have too many or too few G1s, and that is where positive and negative charge come from. Objects such as a magnet, electromagnetic coil, battery, and capacitor can store G1s in the forms of a magnetic field. Of course, they can also store them as orbitals, but that's not the main point of the electromagnetic coil and battery. The G1 orbitals exist in all objects. Charge is having too many or too few G1 orbitals in a static charge. This bottom line is the static charge. This is the dynamic charge. Okay, my name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.